Okay, let's apply our recent learning about the chi-square test to a typical biology problem. It's very, very common to look at inheritance patterns with some suspected set of parental genotypes and to make predictions about what offspring might look like. So let's take a look at that kind of problem. Um, so there's a cross here that's suggested about plants being either normal height or dwarfed height, dwarf sized. And we're going to cross two heterozygous plants, big T, little t, crossed with big T, little t. Because you're familiar with Punnett squares, you'll understand what all this means, and you'll see that there's a 75% chance that the offspring will wind up being of normal height, and a 25% chance that the offspring will inherit the two recessive alleles from the parents and wind up being a dwarf. So one thing for us to note here is that since the chi-square test really gets us thinking about what our assumptions are, and if we get a chi-square number that's too big, we have to revisit our assumptions. Let's take a look at what assumptions are made in this one problem. Okay, so we're assuming that we actually know the genotypes of the parents, that and in fact that they're both heterozygous for height. We're also assuming that it's established that big T is the dominant allele over little t. Um, Another assumption here is that height of the plant is governed by just one gene that has just those two versions, big T and little t. Those may seem very reasonable, and probably are, but we'll run a test, and if our chi-square number is too big, we might have to revisit some of these, or at least one of them. So here's a possible product from this cross, okay? So we're going to allow a large number of plants to be, developed from these parents, okay? And what we wind up with, out of a total of 525 plants, we wind up with 373 normal-sized plants and 152 dwarf plants. So I don't know about you, but that doesn't immediately look like a 75-25 split to me, but that's the whole point of chi-square test is to check, okay? So let's do the numbers, okay? So let's take a look at the normal plants, okay? We expected 75% of the 525 to be um, normal sized plants, and that would be 394. We were short of that, 373, and so our chi-squared numbers observed minus expected, that's the difference of 21, that gets squared, gives you something over 400, and when we divide by the expected value, we wind up with a contribution to the chi-squared number of 1.12. That's the normal contribution. And then what about the dwarf plant contribution? Well, it's going to be 25% of 525. That calculates out to 131. And we wound up with 21 more, not surprisingly. We were 21 shy here, so 21 on the plus side here. So again, we square that, we get something like 441, and we divide by 152 to get a number, a chi-square contribution of 2.90. So we're just about at the point where we can calculate our chi-square number. Our chi-square number for this experiment, oops, excuse me, uh, let's take this out. Sorry, that was left over from before. For this experiment is 1.12 plus 2.90 for a number of 4.02. So you may recall at this point we take that number and we have to bring it to our chi-square table. So let's do that. Here's our chi-square table. We have two questions we need to ask. One is how many degrees of freedom are there? And since there are only two outcomes, tall and short, there's 1 degree of freedom. So we'll look in this column right here. Okay, that's our target, 3.84 or 6.64. Well, we calculated a chi-square number of 4.02, and that's larger than 3.84, but it's smaller than 6.64. So how do we interpret this? Well, this is what we say. we say that here's our conclusion. With 95% confidence, we can reject the null hypothesis. The null hypothesis is that this cross follows a 75-25 split that's expected of two heterozygous parents. There's nothing that's the normal outcome, if you would, in a sense. So either our assumption about parentage is wrong, or our assumption about inheritance is wrong, or the experiment was sloppy in some way. So what do we mean about parentage? Well, parentage being wrong is maybe somehow the parents were not heterozygous. Maybe there was some other combination. I'm not sure that would hold up, but we'd have to look at that. Maybe our assumption about inheritance is wrong. Well, that's a harder one to think about, but maybe it's not just governed by that one allele. Maybe height is influenced by some other genes. Or maybe the experiment was sloppy in some way. Maybe out of that 525, there were 50 of them that maybe came from homozygous dominant parents, or no, I should say homozygous recessive parents. So we had an excess of the dwarf plants. Somehow we included those in our count by mistake. So something's not quite right. But what we don't know exactly what went wrong, but what we can say is that these results do not seem to be just due to random variation around our expected outcomes, but rather something else is going on, and we'd have to go back and really review our experiment. Okay, so that's one way of using the chi-square mathematics to kind of check results in biology. We'll look at a couple more soon.